but I'm sure it'll be great anyway.
Hello. Yeah. Hello, everyone. First, I'd like to thank the organizers for having such a great conference and for giving me this opportunity to give a talk here. And I'll also like to thank PyLadies because they gave me the money to come. So thank you, PyLadies. You're awesome. Thanks. So my name is Viviane. I'm an assistant professor at Université Paris Sud. I'm a mathematician, I'm a computer scientist, and as you can see, I'm very serious about Python. And so today I'm going to give this talk. It's called Experimental Pure Mathematics. And so it's odd, right? Because it's experimental and pure mathematics in the same sentence. So most of you, you're like, yeah, that's kind of weird. You may be wondering, how can you do experimental pure mathematics? So that's to answer this question that I'm here. And the reason I'm here is because last year was my first PyCon, and I went there, I was amazed by the people. Like, I met so many different people doing lots of stuff. And when I was telling them that I was a mathematician, they would always assume that I was an applied mathematician. And I was saying, no, I'm not. I do pure mathematics. And none of them had any idea why I would need to code to do pure mathematics. And I explained it to lots of people last year, and it gave me this idea of this talk for this year. So I'm back this year, and I'm going to explain to a bunch of people at once, so it's going to save me lots of time. So I will start with a question. What does pure mathematics look like? Well, first, let's give you one answer here. It's an image borrowed from a book from Cédric Villani. So he's a French mathematician who had a field medal, so he does quite serious mathematics, right? And this image, I feel, is what people usually picture pure mathematics. So it's lots of weird symbols, complicated equations, like integrals. That's really says pure mathematics. And often, some of the time, I guess pure mathematics look like this. It looks like this for Cédric Villani's work. But I happen to work in a very different area, and for me, it's really rare that it actually looks like this. It's why I had to borrow Cédric Villani's picture. I tried to took one from my papers, but none of it looked like this. So here's what my mathematics look like. This is an actual picture of my research draft. And you see, it's really different, right? There is no equations. There is no integrals. And what you see is all these little weird drawings, like trees, graphs, stuff. And this is what I do. I spend like tons of time carefully drawing this. I kind of look like a maniac when I do this. But it's what I do. I try to understand stuff about it. And I guess this makes you curious. And I'm going to come back to this later and explain to you a bit more of what is my research. But for now, I'm going to pass to a next picture. This is half of my time, okay? And the other half is this. It's coding. So half of the time I do weird pictures, and half of the time I code. This is my research. And this is draft code. This is equivalent of the picture you just saw. So it's kind of badly written. I don't put any comments into it. And the same way that, I do my drafts, and at some point I end up having theorems and proofs, then I write a nice paper to share it with the community. The same is with code. Like, I write some draft code for my research that I need quickly, and at some point it becomes something that could be useful to others, and that's where I share it, and I share it through the Sage software. So this is code taken from the Sage software. Sage is a mathematical software. It's open source. It's written in Python, and it's been built by researchers. So, and here you see, I put the head of a file, and what you see is mostly comments and mathematical references. And the way I see things, Sage is mathematical content. The same way as we have mathematical content in papers and theorems that we put on journals, we have also mathematical content into Sage, and it's written in Python. And so you should maybe know about it, that it exists. So this talk is not specifically about Sage, but Sage is really the way I knew Python, and it's my day-to-day research tool. So this is what I'm going to use today to show you. So now I've introduced a bit the subject, but still you have no idea what I do. Still you have no idea why I need code. To explain this, I will need to tell you a little bit about my research area, which is combinatorics. So first of things, combinatorics is really, really, really cool. You don't know about it, maybe, and if you knew, maybe you would have had a different job. Really, honestly. I don't even understand why people in mathematics do other stuff. Well, so what do we do in combinatorics? I will give you an analogy for you to understand our purpose. So, number theory. What do people in number theory do? Well, numbers first. Numbers, I guess you all use numbers. Everyone uses numbers. If you do science, you use numbers in many, many different ways. Most of the time, if you're not a number theorist, you use numbers because they mean something to you, and you use them. You really use them. So you look at what they mean. Maybe they have some kind of signification in the real world, like if you do biology or if you do, I don't know, geography or something. But number theorists, they don't care about what signification. They care about the numbers themselves. They study the number for themselves. They try to understand them, the structure. And maybe it can be useful for the people using the numbers out there. Well, combinatorics is the same, except I don't study numbers, I study different kind of structures. The structures I study usually come from computer science, like graphs or trees. If you do like machine learning, if you do big data, you use graphs, right? But you don't, you use them with a purpose. But we can also study graphs to understand, without a purpose, the structure of the graphs. And this is what I do with graphs sometimes, but mostly with trees. And trees are also a structure that you will find in lots of areas. So I'm going to give you an example, and I'm going to pick my favorite object, which is a binary tree. So it's really, really a great object. There are many things that you can do with binary trees. So it's quite classical. If you've studied computer science, you may have seen binary trees in an algorithmic class. You know, when you study binary search trees, for example, they come up in algorithms. They come up as data structures. They come up in machine learning sometimes to have some algorithms using this. There's this principle of binary trees. You have this root. So here's the top thing here, and then it divides into two subtrees, left and right, and it does this like recursively. And so this structure is really clever, and it can be used in many ways. So my job is to study the binary trees to understand their mathematical properties. So what is it, the mathematical property of a binary tree? Well, an easy one. You can count the white dots here, and you have like 11 of them. It's not like it's exactly 11 of them here. But of course, I could have made another one. Here's another one. It's also a binary tree. It also has 11 white dots. So first question, how many binary trees with 11 nodes? Well, you can start trying to count, but it will take you some time because there are 58,786, one of them. So you see, it's a lot. And here maybe you start to understand why I need my machine, because even for me, drawing 58,786 binary trees is boring. So, and I'm lazy, so whenever my machine can do something, I just ask my machine. And drawing binary trees is easy. It's an algorithm. You can just tell it, and it will do it. And much faster than I do. And so this is the first kind of question you could ask. Another question, now that you know there are that many binary trees, if you pick one, like randomly, in this big set, what does it look like? Can you say something about it? This is a mathematical question about binary trees. And last question here, which is kind of my favorite, is that, okay, binary trees, you have 58 and blah, blah, blah of them. some other things that are somehow related to them? And the answer actually to this question is yes, there are. And there are so many things that are related to binary trees, so many structures that you wouldn't even think. Like if you take, I go faster because, well, you know, they took my time off. So I'll go straight to the demo. And the demo, you can download it actually. I will be using a website called Sage MathCloud. If you want to know more about it, you can come and ask me a question later. So here that. It's the right one. And if I do this, yeah. So why do I need to do some Python? Well, I need to code this object. And these objects are coded into Sage. And so the question I was just asking to you, they're here. So here is a binary tree in Sage. So really, it's an object to work with binary tree in a mathematical way. And I can create the binary tree, and I can show, like, view it. Yeah, check. And I can ask questions about it, like how many nodes does it have? It says 11 here. How is it like deep? Like it says it has a depth of 5 because you can do 1, 2, 3, like you can do 1, 2, 3, 4, 5, like going down. It says it's not a complete binary tree. This is another property that you could test. It's just examples. There are a bunch of properties you could test on binary trees in Sage. I can create the set of all binary trees, and it tells me that there are an infinity number of them. Well, yeah. But I can also create the set of binary trees with a certain number of nodes. So like binary trees of size 2, and it says there are 2 of them, and I can draw them. So here they are, my 2 binary trees. Now this one is easy, you know, 1 left, 1 right, okay. I could have figured that out by myself. I didn't need my computer. But then sometimes it becomes a bit more complicated, like binary trees of size 3, there are 5 of them. It didn't show the last 2 ones. I won't execute it again because I'm afraid that the internet connection is not really good, but it can tell you the 5 binary trees of size 3, it will show them to you. And then you can ask more questions, like, really cool one, how many binary trees of size 5? 42. Wow, this was the question. I don't know why everyone is so, you know, wondering about that. I knew that for a while. And here I am, like, binary trees of size 11 cardinality. So the truth is, it doesn't create all the binary trees here. It's cheating, because there is a nice formula to count the number of binary trees. Here you can see, I just count the number of binary trees for I below 10, and it gives me this list of numbers. And when I have this list of numbers, then I can try to figure out the formula. And this one is easy because it's a really well-known one. So when I see it, I say, oh, that's it. It's called the Catalan numbers for those who are interested, and they're like magical numbers in combinatorics. And actually, Sage knows about it. So if you look into, no, that's not what I want to do. This is not my computer. And this is Windows. Come on. It's PyCon. So Sage knows, right? It says cardinality, it uses Catalan numbers. So a good thing about Sage, you see, I put this question marks here and it tells me the code inside it. That's a good thing about being open source. So I know how it computes them. But of course, if I had a more complicated structure, I could also code it into Sage and then generate all the objects and then see the numbers and try to figure out the formula by myself. That's the idea of it. Experimenting, that's where experimenting comes. I have some ideas of general mathematical object. I put them into Sage, and I ask my computer questions. The computer gives me answers, and then it's my job to prove the answers right. But if I didn't have my computer to answer my question, I wouldn't even know what question to ask. I wouldn't even know if it was true or not. Here, I only prove things that I know are true, which is much easier. So like here, this is an easy property that you could think about binary trees. It's like counting the number of trees that are the maximal depth. And it's not difficult to figure out that there are 2 to the power of n minus 1. But even if you're not sure about it, well, you could just ask the question first. Okay, is it the right answer? And it says true. And you know, when I did it like yesterday, I actually got it wrong. I had put n here instead of n minus 1, and it told me, no, it's not, it's false. I'm like, okay, right, it's n minus 1. And to come back to the question of random binary trees, this is a nice thing. You were wondering, what does random binary tree look like? This is exactly the kind of stuff you want to experiment. So here you do. I have this little function that's doing random binary trees. Well, it doesn't want to show them, but there are random binary trees of size 11. So it's exactly the algorithm. It's like picking one in the, like, with uniform probability, like any of them with equal chance. But you wouldn't say much, like you see them and say, yeah, what do they look like? I don't know. But here's the second algorithm, which is quite interesting, because now instead of picking one, I pick a word, and I do some kind of binary search tree insertion, if you're familiar with this algorithm. So it's something that happens in real life, actually, that's binary search tree insertion thing. It could happen in many sort of algorithms. And here it gives me a binary tree at the end. But it's not the same, because you see, I can look at the mean of the depth of the binary trees when I do my first algorithm and when I do my second one, and you see it's not the same. Completely different. So a random binary tree is much more like a big branch. But when you do, if you pick first a word and do a binary search tree insertion, then you get more like a bush or something. And this is something that you can prove. But to have even the idea of proving it, you would need to do this kind of stuff before. Because then the computer tells you there is something there. There is something to prove. Even before trying to have like the mathematical proof to it, like the knowledge. And it's how mathematics works. Even for those who don't do code, they first have to have the intuition of it. The computer is just helping my intuition. I still have the intuition, and then I give it to my computer, and it gives me a result that I can prove. So to prove you that I'm not bluffing, here, well, yeah, I'm full screen, doesn't like it, F11. Here is some kind of common work that I'm doing with my co-author, and where I do some experimentation. So it's with trees and some other stuff, so I won't come into the detail, but this is actual tests that I run with my coworkers to show them that the algorithms we're working on are good. And see what I do? I do a list of objects. I'm trying to transform objects into other objects, and I'm trying to see if it's still working. And then this is something I do a lot, like printing lots of true statements, to be sure that my property is true for like everyone. And it says, yeah, true, true. And then I use the all, of course, all, blah, 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 because it's better. But I like to do the printings of the true because I like to be sure that it's actually testing all of them. I'm never completely sure when I do it with only one true thing. And here they are, like this, my objects. And I print them, and I do nice little algorithm about them. And after that, exit full screen, yes. And then go there, I guess, offline. Sorry for this, it's because I didn't, yeah. And I think this is a paper. Yeah, this is a paper related to this, what I was showing you. So then it turns into an actual paper. And it's a paper that has been published, and which is going to be presented as our annual combinatorics meeting. So it's really the way I work. It's not just for PyCon. I wanted to share to you the way I do my research and where is Python involved. So I'm going to finish with one slide, which is this. Says, if you want to learn more about Sage, we're having Sage Days during the sprints. We have talks in the morning at the UCAM, and in the afternoon we'll be there to sprint. So depending on how much you're interested, you can join us for the talks or just come talk to us during the sprints. We're a bunch of Sage people here this week, and we would be really happy to answer your questions and talk to you about our work. Thank you very much.
Thanks, Viviane. So we've actually got time for a question or two. If anyone has a question, you can line up at the mic there, and we'll wrap up in about 5 minutes.
Okay.
So you said that you would use Sage to figure out what was true before you actually proved it.
Yeah.
Have you ever been misled by a bug in Sage?
I've been misled by bugs in my own code. I've been misled by bugs in my own code. Sometimes I believe something, and then I read back my function, and I realize I wrote something completely not right. But the good thing is, if you don't trust the code in Sage, then you can look at it to see if it actually does what you want to do, because it's open source. So it didn't happen to me. I know it could happen to people. I know it happened to people before. It could mislead you. But then you find the bug, then you talk to the people, and then the bug is fixed, or you fix it yourself.
Great talk, thanks.
Thank you.
One issue that we have in the place where I work is, we'll write a new algorithm that's going to process, some massive data set, and we want to know, is it going to be true for every row? And we end up getting into the deep mathematics and writing a proof and stuff like that. And it's hard, and it doesn't work a lot. Can Sage help us solve that problem? And do that more efficiently?
I'm not a specialist of really big data sets, because I usually stop. Like for combinatorics, you don't need, it grows quite fast, but you don't usually need to test on so many things to be sure that it's true. But I know lots of people in Sage are really interested in getting better performance and doing lots of things with Cython, doing lots of things with parallel work. So I would say just now it really depends on what you're working on. But if you're interested in trying to improve this, then you can talk to Sage people, and you would find interested people in front of you trying to solve your problem.
Thanks very much for your talk.
Could
you speak briefly as to how effective Sage is for doing calculus and linear algebra?
Calculus and linear algebra, I'm not a specialist into this either. I never do this, honestly. It does all the basic stuff, that's for sure. There is a book in French that helps you go through it and see, like for all the undergraduate level, for example, it does everything that you would need. For more advanced stuff, then there are still some stuff that are on Maple, it's not working into Sage, but people are really Sage is built from good. It depends how many people want it into Sage. If you want really hard to have it into Sage, then you code it into Sage, and then it's in there. That's the good part. If nobody ever wanted to put it there, then it's not. That's how it works.
Okay, I think that concludes this talk. Thanks so much, Viviane.
You're welcome.